What is going on, everybody? Mr. Martin, what a wonderful time to be back on this brand new lesson for you. We're on 4.2. We're going to talk about data distribution. Okay, in the previous lesson, we talked about how to find the different measures of central tendency. Today, we are looking at how this data is distributed. We're going to be talking about things that are symmetric or asymmetric. Okay, and we use these shapes. Remember, symmetric is like a mirrored image, meaning the same on both sides, and then asymmetric means that they look a little different from one side to the other. But we want to talk about this in relationship to the mean and the median. So make sure you are committing these pieces of vocabulary down to your memory banks because you will need to be able to recall them. All right, so we do know that statistics is about data, or we use data when we talk about statistics. Today we're going to analyze some graphs because graphs provide representation of the distributions of data. And these are used to understand the data and answer any questions that we might have about how they are distributed. All right, so make sure you go ahead and write that down. Let's take a look at these different types of graphs. We have this first one here on the left. This is what we call a histogram. Here's a brief little description of it. We have a graph of data that groups based on intervals and represents the data in each interval by a bar. So not to be confused with a bar graph. Remember, a bar graph will have space in between the bars. This is just one fluid motion, meaning that we have these intervals down here. So also remember, a graph, it needs a title, right? We need to know what we're talking about. In this case, this graph is representing the different ages for population in Kenya. Okay, so we have down here our values for ages. So if we looked at this first bar right here, this one going all the way down, right? This first interval is going to be from 0 to 5 years, and then the next bar 5 to 10 years, and so on. So when we have many pieces of data, okay, a histogram is going to be good to represent lots of data like that. All right, the next one that we're going to see is a dot plot. Okay, so we have this number line down here, and then we have all of these dots. So this is saying we're talking about shoe size right here. Let me go ahead and highlight that for you. So what this graph is talking about, it is saying that, hey, from the sample that we took, anybody that's shoe size 4 to 12, we had 2 people that have a size 4, 1 person that has a size 5, a 6, and here we got 1, 2, 3, 5 people with a size 9. So this just represents that sample size of people and their shoe sizes. So it's always good to think about the data and to ask different questions, have different discussions, because remember, there is a lot of ambiguity with statistics, right? You know, we can argue many different things, and a lot of it is left up to the interpretation. So one thing that could help us, you know, make this a better titled graph, if we look at these types of sizes, we might want to say US shoe sizes, right? These look like shoe sizes that we would find in the US. If you look at Europeans, if these were male sizes, they would be in the 40s. For example, Mr. Martin is a 10.5, and I believe I'm a 44 2/3 in European size, and I think I'm a 285 in Korean. So knowing that this is US shoe sizes could have been helpful. Another thing too is, if you look, there are no half sizes here. These are all whole sizes. So maybe having our number line with half sizes might have been a more descriptive type of dot plot. But if you don't have that many pieces of data, dot plot is useful. If we had like something like this, we would probably not want to use a dot plot. All right, and then the final one that we have is the stem and leaf. This one is talking how many minutes it takes to run a 5K. Okay, so remember, the leaf is always going to be 1 digit, the last digit, okay? And then our stem, it can be more than 1 digit, and a stem and leaf plot is typically only as good as its key, right? We need that key to be able to understand what we're talking about in that stem and leaf plot. So here it says if we have a stem of 2 and a leaf of 7, that value is actually 27. So if we had this 3 and this 1, based off of this 2 and this 7, we would know that this is the value of 31. So it is important to be able to read what the stem and leaf plot is telling you, and we look at the key to help us do that. All right, so here is the meat and potatoes of our distribution. Okay, so there is one thing that I want to talk about before we dive into this. Here, let me pull up some text right here. When we talk about distribution, okay, let's do this here. The median, so you guys should write this on your notes, is the true measure of our center. Okay, so what this means, right, is sometimes, and we learned this in the previous lesson, that certain values may change the average. And remember, the average is the mean. Okay, so when we look at our distribution, okay, we have these 3 main types right here. When we look at our distribution, we want to understand that the median is the true measure of our center, and you guys will see why here in a minute. Okay, so one other thing too, let's start with this one in the middle. This is what we call a symmetrical distribution. This is also called a normal distribution. All right, so I'm gonna type this in. This is also called a normal distribution. Okay, so let's have that here. And then another term that you might have heard is also called a bell curve. Okay, let's go ahead and type that in. So when we have this symmetrical shape, okay, it looks very even going down on one side as it does to the right side. This is what we know as a bell curve. It is also called a normal distribution or a symmetrical distribution. And if you take a look, okay, we can see that at the tip of our graph that we are falling to the left and we are falling to the right, and everything looks pretty even. This means that the bulk of our data points are right here on this line. Okay, and then the other thing that is important, when we have a symmetrical distribution, that means our mean is equal to our median, and it's also equal to our mode. So all of these measures right here are going to either be an exact match or very, very, very close. So let's say that our median was 5, okay, just a generic value. Our mean would maybe be something like 5.3, something very, very, very close. Okay, so this is what we call a normal distribution. All right, let's go to the one here on the left. Okay, I'm gonna type this one in also. When we have a positive skew, okay, this is also known as skewed right. Okay, so you might have heard of skewed right. And what this tells us, okay, if we take a look, we have the hump of our graph right here, and it looks like it is falling to the right. So it is skewed to the right. And the reason it's called a positive skew is because on a number line, right, we read from left to right. As our numbers get bigger, that is positive. As our numbers get smaller to the left, that is negative. So this is what we call skewed right. Okay, and then let's take a look here at these measures, right? Remember, our median is a true measure of center. We want to imagine that that median is always staying put. So as we skewed our data to the right, okay, this is where the bulk of our data is, and we have a few large pieces of data down here. When it skews to the right, look what happens to the direction of the mean. Here it was in the middle. Now the median is here, and the mean is further to the right from the median, is on the right side of the median, meaning that it is of a larger value. So one way that we can remember this, we can say that, hey, when we are skewed right, okay, the mean is greater than the median. Okay, if you look, it shows that the mean is now larger than the median. Okay, so let's just assign this a generic value just so our brains can understand it. Let's say that the median here was 5.5. When we are skewed to the right, our mean might be something like 7. Okay, so that is skewed right. All right, let's also take a look at this last one here on the right. We are looking at a negative skew, and if you haven't guessed it already, this is what we might call skewed left. Okay, and then let me just hit enter here. Skewed left, this, if you take a look, the mean is now to the left of the median. So this is saying that the mean is less than the median. Okay, so when we are negative skew, okay, let me put this negative sign here and this positive sign here. If we are skewed to the left, the graph is falling to the left. Our median is our true measure of center. That stays put. The mean is now moved to the left. Okay, so these types of distributions are paramount. Make sure that you have a way to commit this to memory and understand what would be greater or less than based on the direction of your skew. All right, very good. Okay, so we have this dot plot. Okay, this one is talking about goals in a hockey game. You have your calculators. Let me go ahead and pull mine up. One moment. All right, so I got my calculator up here. It wants us to find the mean and the median. Remember, this is a dot plot. Let me just go ahead and put this right here. So remember, this is how many ones we have, how many twos, and so on. So let's go ahead and edit our data. Let's pop this up for you guys. All right, so let's go ahead and enter this data. So how many ones do we have? We got one of those. We have 1, 2. We have 1, 3. Looks like we have 8 5s. So I'm gonna go 5, 5, 5, 5, 5, 5, 5, 5. We have 6 6s. 1, 2, 3, 4, 5, 6. 2 7s. 1 8. And 1 9. All right, so it looks like we got 21 pieces of data. Now that we got that in, let's go ahead and hit stat. We want to go to calculate, 1 var stats, and then enter, enter, enter. We can find this data. Oops. Where did my screen go? There we go. All right, so it looks like we have our average is the mean 5.38, and we have a median of 5. So 5.38 and 5. So let's write that in. We got X bar 5.38, and then our median is 5. So if we look at the shape of this, okay, looking at our values, we got 5.38 and then a median of 5. Remember, the median is the true measure of center. This average is not that far off from 5. So I would determine, if I was trying to figure out the shape of this distribution, I would say that this is a normal distribution. Remember, look, the bulk of our data is between 5 and 6 goals. Okay. We have a median of 5. This value is not that far off. And remember, we're only talking about 1 through 9 goals. So I would say that this is very close to being exact, which would make this a normal distribution. All right, so let's take a look at the next example. Okay, this says tell whether the following distributions are more likely to be skewed left, skewed right, or symmetrical. So go ahead and pause the video here and take a moment to think of what direction these might be. Maybe sketch them down, and if I came up with something different, then go ahead and change it. But I'll give you a moment, pause the video, and just think about that. All right, welcome back. Hopefully you thought long and hard about it. Okay, this first one, I'm going to let you know this is actually a skewed right graph. Okay, so the reason this is skewed right, let's think about it. Okay, the mileage on used cars that are for sale. Let's say this is the high end of mileage at 200,000. Okay, when you buy a car, most of the time you want to buy a car that is reliable. So people aren't really going out buying cars that have 200,000 miles on them. Typically, people are buying cars that are anywhere from, I don't know, maybe 10,000 to 20,000 miles. Okay, so the bulk of our data is going to be in this area here where this hump is, and then it's going to start tapering down because people aren't really buying super duper old cars. Okay, and then also back here, you're going to start off, not many people are buying cars with very little mileage because those would be considered newer cars. So this one is going to be skewed to the right. All right, and then the height of the population. A lot of people get this one. Think about the term average Joe. Okay, remember the word average. We're talking about a normal distribution. So if we think about the height of people in a population, you know, you will have those few people that are really short, and then you're going to have those few people that are extremely tall. But for the most part, everyone's going to fit within this average height right here. So the bulk of our data is going to be smack dab here in the center. So this is going to be a normal distribution. All right. Okay, let's take a look at another example. We have this mean or this histogram and the stem and leaf plot. We want to estimate the mean and the median from the graph and state its distribution. So if we take a look at this histogram, it looks like the bulk of our data is right here, and then the information starts falling to the right. So if you haven't guessed it, yes, this will be a skewed right. So we can write down here, skewed to the right. Okay, then it's a good idea to think of finding our median first. Okay, so this is the most amount of our data right here in this high point. Looks like we're between the ages of 30 and 35. So maybe if we had a line going down here, maybe we would be somewhere around 32 or 33 years old. So with that being said, if we are skewed to the right, remember that means it is pulling the mean upwards, so our average needs to be a little bit bigger than 33. So I don't know, maybe something like 35 would be a good estimation for that. Alright, so here on the right we have minutes to run a 5K. This is our stem and leaf plot, and if you notice, the stem is getting larger as we go down. This is done vertically. We do kind of want to look at this horizontally, so you might need to kind of adjust your eyes and flip this image to where it looks like it is horizontal. Okay, meaning that we would want this to be like 1, 2, 3, 4, and a way that we could do this would be visualizing this going downward like this, counterclockwise 90 degrees. Let me post an image here just so you can see how it would look if we were to flip it. So let's go ahead and do that. I'm gonna drop this right here. Let's get rid of this right here. Okay, so imagine that we're looking at it like this. Remember, our key right here says the stem is 2 and the leaf is 6, standing for 26, meaning 26 minutes. Okay, and then we want to kind of figure out this distribution. So the bulk of our data is right here in 2 and 3. There's only one on the left. There's a few here on the right. But I would go ahead and guess that this would be symmetric. Okay, so this is going to be a normal distribution. Okay, and then an easy way for us to find our median with the stem and leaf plot is to actually count up how many pieces of data we have. And remember, we're going from left to right, and we actually also go from down to up. So this would be our first piece: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So if we have 23 pieces of data, okay, that means we are an odd data set, so we're actually going to have one middle number. So if we subtract that 1, that's going to give us 22, and then we want to split this in half. So 22 divided by 2 is going to give us 11. So that means we would have 11 on each side, and then our number would be in the middle. So let's count that up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's my 11 to the left. This is my middle number, and I would have 11 to the right. So using our key, we have a 3 and a 1. That tells us that our median is 31. So if we were to guess the mean, we could say 31. It looks like it might slide a little bit more to the left, like the bulk of the data is to the right. So I would estimate an approximate mean of something a little bit less than 31, maybe something like 30.2. Okay, so remember, you're going to be doing approximations. Just make sure your approximations come off as sound and not extremely far off. All right, and then the last piece that we have, this is something very good to remember. These are the effects that outliers have on our distribution. If we have an outlier, okay, this will change the mean, okay, and it's going to pull it towards the value of the outlier. So if we have a really large outlier, it's going to pull it to the right and give us that skewed right or positive skew. If we have a really small outlier, it's going to skew to the left and be a negative skew, okay? The outlier will not change the median, okay? And with the standard deviation, okay, if you do have an outlier, whether it's a big one or a small one, this will always increase the standard deviation. Because remember, the standard deviation talks about the variability between the data points. So if you have that outlier that's affecting the mean, okay, that's going to create a bigger range, okay, and that's also going to create more variability between those data points. So if we have more variability, we're going to have an increase in our standard deviation. So the standard deviation will not decrease, it will always increase. All right, so that is my lesson. Hopefully you enjoyed it. Please do some practice. It takes a little while to get good at these and really wrap your head around what we are talking about. So make sure you commit that vocab to memory. Please reach out for help if you need some. Ask a friend, ask a parent, ask a teacher, ask somebody. I'm sure they're willing to help you. I always recommend it. And I always recommend doing the practice. It is very, very important. So I will catch you on the next one. I hope you enjoyed it. Peace out.